Hey guys, so I'd like to begin by talking about solubility reactions and KSP. So what is a solubility reaction? Well, usually in general chemistry, the second semester of general chemistry, when we talk about a solubility reaction, we're talking about a solid mass inside of a solution, and generally the solution has the solvent water, so it's an aqueous solution, and this solid mass is dissolving, right? And we've all seen this happen. If you drop a cube of table salt into water, it's going to dissolve. And that is what we refer to as a solubility reaction. And so I wrote up an example here of a situation you might see. So for example, silver bromide solid. Let's say we've got a solid mass of silver bromide in an aqueous solution here. Well, what's going to happen when we put this into solution? Well, silver bromide is actually generally considered insoluble in water, but that just means it's very slightly soluble. It's not soluble like table salt is in water, where it completely dissolves at room temperature. But silver bromide is still going to dissolve to some extent, right, in water. So you're going to have silver ions, Ag+, and bromide ions, Br-, slowly ionizing off of this silver bromide solid mass. And again, that is what we refer to as a solubility reaction. So if you write that out as a chemical equation, you're going to have silver bromide solid goes to Ag+ in the aqueous state and Br- in the aqueous state, or silver and bromide. So you can see here that silver bromide as the solid mass, as that compound here, is in the solid state. Whereas these ions that have broken off of the solid mass are in the aqueous state. This means that this is undissolved and these are dissolved in water. So as with any chemical equation, we can write an equilibrium constant and an equilibrium expression for it. So the equilibrium constant for solubility reactions we refer to as KSP, where SP stands for solubility product. And that makes sense, right? These are solubility products. And this is just like an equilibrium constant for any other situation. You know, you think about Ka, that's the equilibrium constant for an acid. Kb, that's the equilibrium constant for a base. Kp, that's the equilibrium constant for pressure, for gases. And you can come up with equilibrium constants for pretty much any process, any chemical process. And all it means is the concentration of the products to their respective stoichiometric coefficient powers multiplied together over the concentration of the reactants. But remember, for pure solids and pure liquids, we do not include them in the equilibrium expression. So here in a solubility reaction, for example, if we have a soluble compound or a solid piece of matter in a solution, we're going to consider that in our equilibrium expression to be 1. So really, you know, if we say the KSP for this reaction is a certain value, and we want to describe it in terms of the reactants and products, well, we can look up on a table that the KSP for silver bromide is 5.4 times 10 to the negative 13. But in terms of the products and reactants, it's going to look like this, right? We've got concentration of silver ions, concentration of bromine ions, and those are the products. And then over the reactant, which we know is a pure solid, so we'll include that as a 1. And another important thing you can do for these solubility reactions is draw a Rice table. So Rice tables, remember, stand for reaction, initial, change, and equilibrium. So they describe what happens to a chemical process as it reaches its own equilibrium. So here you write your reaction, which we've already written, the initial amounts. So we're going to assume, you know, that we don't have to deal with solids and liquids in these reactions, but the initial amounts of products we're going to assume to be 0, because we're going to assume we started out all with this solid compound. None of it had dissolved yet. So these are going to start out with 0 as our product, 0 molar. And then our change we know is going to be, you know, if this were to be included, we would have -x, but since it's a pure solid, we're not going to worry about it. Plus x for each one of our products. And then equilibrium 0, plus x, 0, plus x, we end up with 2 x's down here. So our KSP, or our equilibrium expression here for this process, is going to be x squared over 1, really. We didn't write anything here because we don't include the pure solid. So if we know our KSP, 5.4 times 10 to the negative 13, we can simply set that equal to what we obtained from our Rice table for our equilibrium expression. And really, all this represents, KSP equals x squared, is this, right? Because we don't know what the concentration of silver ions and bromide ions are going to be at equilibrium. So we represent each one of them with a single x, a 1x, because their coefficients are 1, right? So then if we know the KSP, we can solve for the concentration of these ion products. And when you solve for that on your calculator, you'll simply take the square root of 5.4 times 10 to the negative 3, and you'll get the final concentration of both the silver and the bromide ions should be 7.35 times 10 to the negative 7 molar at equilibrium. So what does this mean? Well, not only is this the concentration of silver ions and bromide ions at equilibrium, it's also the amount of concentration of silver bromide that we lost, right? This much silver bromide went in to silver and bromide ions, right? So we call this the solubility of silver bromide. It's the concentration which dissolved from the solid matter in the solution. Alright, so these edits I've made to the board here in blue ink are supposed to illustrate something called the common ion effect. So the common ion effect is essentially an application of Le Chatelier's principle to solubility reactions. So what happens in a solubility reaction? Let's remind ourselves. Well, we've got a solid piece of matter dissolving into its ions, right? And Le Chatelier's principle says that the reaction is essentially going to shift based on outside forces. So silver bromide, for example, if we were to add more of this solid reactant, the reaction would shift to make more dissolved ions. If we were to add more of these dissolved ions, the reaction would shift back to make more solid reactant. So Le Chatelier's principle essentially responds to outside stressors in terms of if you add more of this, it's going to shift it more this way. For example, if you were to take away more of this, it would shift it back to the reactants. So you can think about Le Chatelier's principle as representing this reaction as almost like a pool of water. If I add more water here, it's going to spill over here. If I were to take away water here, it's going to spill over here. So if I take away Br, for example, Le Chatelier's principle says we're going to go more this way. If I add Br, we're going to go back this way. It's going to spill over back to the reactants. So that's a little review of Le Chatelier's principle. And so the common ion effect essentially says that we have a solubility reaction, but in the periphery, in parallel to this solubility reaction, we have another dissolving solute, for example, sodium bromide, making an ion that is common to our solubility reaction here, right? So now in the solution, not only do we have bromide ions coming from the silver bromide, now we have bromide ions also coming from sodium bromide, for example. And I'm just going to say, for example's sake, that this is a 0.7 molar solution of sodium bromide. And we know sodium salts are soluble. So if we started out with 0.7 molar of sodium bromide, we're going to end up with 0.7 molar sodium ions and 0.7 molar bromide ions. And notice how sodium, we don't call that a common ion because it doesn't appear anywhere else. It's not common to any other solubility reaction occurring in our solution. So what would you hypothesize that this is going to do to the solubility of silver bromide, adding in something that's going to produce a common ion? Well, remember we said Le Chatelier's principle says that if we add more of something on the product side, it's going to cause it to spill back towards the reactant side of the reaction, right? So if we add more Br minus to the solution, it's probably going to make silver bromide less soluble, right? Because we're going to push things back to the solid matter, back to the solid reactant. So that's exactly what happens, and I want to show that mathematically. So what adjustments would we have to make to our calculations here to account for this bromide ion? Well, in our Rice table, now we didn't start with 0 molar Br minus, assuming that this reaction had not taken place. Now we have a completely soluble in aqueous solution salt. Sodium bromide is soluble in an aqueous solution. So now we're really going to start out with 0.7 molar Br minus. And remember, this Rice table is only for this reaction, but notice how we're including information from a separate reaction because there is a common ion, right? This reaction is sort of like intruding on this reaction. It creates something that affects this reaction's equilibrium via the Le Chatelier principle. So now we have to add, for our initial amount of Br minus, 0.7 molar of Br minus. And everything else stays the same. For the change, we still have plus x and plus x for this reaction's Rice table. But But now down here we're going to end up with x and then 0.7 plus x. So before, remember, we had KSP equal to x squared, and we were able to solve for the solubility of silver bromide simply taking the square root of its KSP. But now we have this value here. And take a look at this KSP. This is a very, very small number, right? And that's a testament to the fact that silver bromide is not soluble. Very, very small KSP means that very little of this is going into products. But that allows us to use what's called the shortcut rule. And remember, the shortcut rule says that if I take 100 times the K, so 100 times 5.4 times 10 to the negative 13, if that's less than 0.7, then I can forget about this plus x here. And if you do those calculations, you'll see that that is the case, and we can actually forget about this plus x. So now these are our equilibrium concentrations for our expression, and we end up with KSP not equal to x squared, but KSP equal to 0.7x, right? 0.7 times x is 0.7x. And then to solve for x now, we simply divide both sides by 0.7, and you end up with x equals 7.71 times 10 to the negative 13 molar. So this is the solubility of silver bromide in the presence of sodium bromide solubility reaction occurring in parallel, right? Because it produces this common ion that shifts this reaction back to the reactant, thus making silver bromide less soluble. And that makes sense, right? The solubility went way down. Before, without the sodium bromide, it was 7.35 times 10 to the negative 7. Now it's 7.71 times 10 to the negative 13, a number smaller by many orders of magnitude. So hopefully that makes sense. Okay, so we just talked about in the last clip how adding a common ion to a solution decreases solubility, right? Well, now I want to talk about two ways that you can actually increase solubility. And the first one is to simply select your solid compound to be a weak acid. And these are all examples of weak acids up here that I've written. And I want to illustrate this with the dissolution or solubilization of calcium carbonate. And so this is a weak acid, and I want you to think about, why would a weak acid be especially soluble? Well, think about what's going to happen when a weak acid dissolves. It's going to make a conjugate base, right? Weak acids make conjugate bases. And remember, we memorized that the weaker the acid, the stronger the conjugate base. So if you've got a weak acid, for example, calcium carbonate, and it creates a strong conjugate base, well, guess what that strong conjugate base is going to do? It's going to go on to react with water and use itself up. So when we use up and take away one of the products, guess what happens? More of our reactants go to the products. So if we have a weak acid that creates a strong conjugate base, which strongly reacts with water, it's going to use itself up, its value and its concentration is going to diminish, so that more reactants are pushed over to products, and thus this is more soluble. So I want to walk through the mathematics of this. So just as a note up here, the KSP of calcium carbonate is 2.8 times 10 to the negative 9. We'll need that because we're setting up a Rice table for the solubility reaction. So again, remember, we're assuming it started with 0 products, and we do not consider pure solids in our equilibrium expression, so I will not worry about this row. This column. So now I add plus x and plus x because these each have a stoichiometric coefficient of 1, and I end up with 0 plus x is x, 0 plus x is x in my equilibrium row. So I can very easily and quickly determine that the solubility of calcium carbonate is going to be this equals x squared, so take the square root of that, 5.29 times 10 to the negative 5 molar. So that is the amount in concentration of calcium carbonate that is going to dissolve. That is the definition of calcium carbonate's solubility. But that does not account for the fact that, again, this strong conjugate base, and remember, you know, it's not a strong base, but it's a relatively strong conjugate base, because if we have a weak acid, the conjugate base is going to be relatively strong. We don't consider it a true strong base, but it's still actually going to react pretty significantly with water to push the reaction forward here. So now if we consider in the math that this carbonate ion is going to react with water, it's going to produce, remember this is a base, so it's going to accept a proton to become bicarbonate, and then water is going to be left over as hydroxide ion. So what we want to actually do here to account for this is to add this reaction to our original reaction to account for what's going to happen with this carbonate going forward, right? So whenever we add two reactions, we add together the reactants and we add together the products. And when you add together the reactants, you get this, and when you add together the products, you get that. And what do we have to do to the equilibrium constants of two reactions when we add them together? Well, if you remember from previous exams, we actually have to multiply them. So I will multiply the KSP for this reaction with the KB of this blue reaction here. So I'll get the equilibrium constant for this resultant reaction is 5.88 times 10 to the negative 13. So I'll then write my Rice table for this bigger reaction that resulted from the addition of these two reactions. And remember, I don't consider pure solids or pure liquids, so I won't worry about these columns. And I'll assume I started with 0 molar of my products here. And I'll get plus x plus x plus x. So my final equilibrium expression will be x times x times x, which is x cubed. So I will simply take the cubed root of this resultant equilibrium constant here that I got, and you get x equals 8.38 times 10 to the negative 5 molar. So now this will be the final concentration of the amount of calcium carbonate that solubilized or dissolved. So you can see here that this is slightly bigger than the 5.29 times 10 to the negative 5. Not a huge amount larger, but definitely a noticeable increase in solubility simply because of this conjugate bases reaction with water going forward, depleting itself, thus causing more of the reactants to go into products. Okay, so we just talked about how if you have a weak acid and it dissociates into a relatively strong conjugate base, that's going to increase the solubility of the solid from which it dissolved, right? But there's a way that we can enhance that and increase the solubility much further. So we know that if we have a relatively strong conjugate base, it reacted with water to a significant extent. But what if we actually put in an acid for this conjugate base to react with? That effect could be much, much greater, right? Because water can act as an acid to some extent, but if we add in a true acid here for this conjugate base to react with, the effect will be that this conjugate base will react to the acid to a much greater extent than it did with water, thus depleting itself very significantly, and thus drawing the reaction towards the products, right? Via Le Chatelier's principle, and thus increasing the solubility of this solid compound. So let me show you how this works, again, mathematically. So let's say we added a 0.02 molar acid to this already dissolving solid solution. Calcium carbonate was thrown into an aqueous solution. It started dissolving into calcium ions and carbonate ions. And let's say we added in any acid that contributed 0.02 molar of H+. Well, we know that that's going to create this parallel or peripheral reaction with carbonate reacting with the H+ to make bicarbonate. And so essentially this is going to work to use up the carbonate, as I said. So now it's going to be depleted and the reaction will be drawn forward, thus increasing the solubility of calcium carbonate. So again, we want to add these two reactions together because they're both happening in the same jar, presumably, and we want to see what the overall addition reaction is going to be here, the resultant reaction. So I've written that here for the R for my new Rice table. And you can see carbonate appeared on both sides, so I crossed that out, as you always should. So our reactants here that we're left with are calcium carbonate and H+. And remember, calcium carbonate is in the solid state, so we will not consider it with our Rice table. H+, however, is in the aqueous state, so we will consider that as a reactant in our Rice table. And then we've got bicarbonate over there, and it is in the aqueous state, so we will consider it. And finally, calcium ions, and we will assume that we didn't start with any products. However, we did start with 0.02 molars of acid because we were told that. So in our change row, we know that this is going to be minus x because it's a reactant, plus x and plus x because they're products, all with stoichiometric coefficients of 1. And then our final equilibrium row is going to be the addition of I and C, so 0.02 minus x, 0 plus x, 0 plus x. And so if we want to set up an equilibrium expression here, we know it's going to be x squared over 0.02 minus x, right? But we need to find our equilibrium constant for this resultant reaction here. And in order to do that, we already have the KSP for this reaction here. We already have that 2.8 times 10 to the negative 9 right here. But we need to multiply this equilibrium constant with this reaction's equilibrium constant, right? Because remember, when we add two reactions together, we multiply their equilibrium constants. So in order to figure this out, you can find the Ka for bicarbonate on any Ka table, and it's simply going to describe the dissociation of bicarbonate into H plus and CO3 minus. And we know that this is the exact reverse reaction of that, right? Where CO3, 2 minus, and H plus are going into bicarbonate. So whenever we flip a reaction, we simply take the inverse of the equilibrium constant. So we can find the Ka and then take the inverse of it. And when you do that on your calculator, you'll get 2.1 times 10 to the 10th power, right? Pretty big number. And so now we'll simply multiply that with the KSP because we added the reactions together, and you get a resultant equilibrium constant of 58.8. Very large, so there is very little chance that we're going to be able to use the shortcut rule. You multiply 100 times this, far bigger than 0.02, so we cannot use the shortcut rule. So you set up your equilibrium expression here, 58.8 equals x squared over 0.02 minus x, so we can't ignore this minus x here because the shortcut rule does not apply. And you see that when we add this acid, the solubility of calcium carbonate skyrockets, right? Now it's 1.99 times 10 to the negative 2. That is way bigger than 5.29 times 10 to the negative 5, right? So you can see here that as a quick summary, one way to decrease solubility is to add a common ion, and then two ways to increase solubility are: number one, pick a weak acid that's going to dissociate into its conjugate base, and then number two, enhance that effect by adding in an acid for the conjugate base to react with even better. Okay, now I'd like to move on to precipitation reactions and QSP. So this should sound a little bit familiar, this letter Q. Remember earlier in the semester we talked about K and Q. And K, remember, is our equilibrium constant, while Q, it has the same form as the equilibrium constant, but it describes a reaction not necessarily at equilibrium. So Q is kind of the state of the reaction at any given point, not necessarily at equilibrium, while K is at equilibrium. So in order to explain QSP, I need to talk a little bit more about KSP. I've introduced it, but I really haven't told you the whole story. So KSP, remember, is the equilibrium constant that describes a solubility reaction. And really it also describes precipitation reactions from the other direction, because a precipitation reaction is really the opposite of a solubility reaction. A solubility reaction, remember, describes a solid compound in a solution dissolving into its ions, whereas a precipitation reaction are dissolved ions in a solution going back into the solid compound. So I want to go through these three scenarios up here to really make it clear what I mean by KSP and QSP. So I want to start with this middle scenario right here. So when KSP is reached, in other words, when QSP equals KSP, when the state of the reaction is at equilibrium, we call a solution saturated with ions, for example, because we know precipitation reactions are ions forming their solid compounds. So in this scenario, we have the exact maximum amount of ions that could precipitate into a solid in solution. If we added a single additional NaCl solid into this solution, it would start to form a precipitate, or a little tiny microscopic piece of solid table salt would form at the bottom of this jar here. So when the solution is saturated, when KSP is achieved, when the solubility reaction is at equilibrium, all ways of saying the same thing, this has the most possible amount of Na plus and Cl minus in it before they start to precipitate, before they make a solid compound. If we were to add a single more NaCl, we would be beyond saturation, and the state of the reaction would be greater than KSP. So you can see here that we added an additional, doesn't matter how many more, at least one, NaCl molecule, and we started to form a solid precipitate, a solid compound in this solution. And we are now beyond saturation. The solution is beyond saturation with Na plus and Cl minus. And you can imagine before we reached KSP, we would not yet be saturated. QSP would be less than KSP. The state of the reaction would be less than saturation. And we would be able to add comfortably more NaCl molecules into the solution before we would worry about getting close to saturation and then finally precipitation. So in a precipitation problem, you'll be given generally 2 soluble salts. So let me go through this one. So in a 1 liter solution, 0.02 molar of NaCl are mixed with 0.02 molar of AgNO3. So sodium chloride and silver nitrate. These are both soluble salts, right? You know that from your solubility rules. And they ask, will silver chloride solid precipitate? So they sort of imply here that you're going to have a precipitate. And if you really want to know what's going on, you write out the full chemical equation. We know that these 2 salts are going to be soluble, so they're going to dissociate into Na plus and Cl minus. This is going to dissociate into Ag plus and NO3 minus. And what happens in general in solubility reactions is that the ions kind of swap partners. So here sodium was paired with the chloride, but over here sodium is now paired with the nitrate. It's switched partners. Over here silver was paired with the nitrate, but now over here it's switched with the, now it's paired with the chlorine. And you know from your solubility rules that everything here is soluble except for silver chloride. Thus it has the potential to precipitate. And really here I use sodium chloride as an example, but generally when you're doing these calculations you're using some compound that's not soluble. So sodium chloride we know is soluble in an aqueous solution, but the same concepts apply. You simply have to get to very, very, very high concentrations of sodium chloride before you would actually see solid table salt accumulating at the bottom of the pot. Okay, so in general how you solve these problems is you start out by figuring out what is the saturation concentration of these ions. What does that have to be? How many ions of silver and chlorine can be in a solution until just adding a single more AgCl molecule would cause a precipitate? So how far can we get to push that cusp of right before precipitation? Well, you set up your rice table as we did before, and we assume we start out with 0 products, and we do plus x, and you can find the KSP of AgCl on a table, and you'll find it's 1.8 times 10 to the negative 10. And solving for x at equilibrium will get you the equilibrium, or the KSP achieve concentrations of Cl minus and Ag plus. And you see that the concentration of silver and chloride at equilibrium in a solubility or precipitation reaction of silver chloride is 1.34 times 10 to the negative 5 molar. So that means in this situation, when KSP is achieved, or when QSP equals KSP and we are saturated, you can have exactly this concentration of Ag plus and Cl minus in solution. If we add a single additional AgCl molecule, we create a precipitate. So now we know that we weren't given exactly 1.34 times 10 to the negative 5 molar Ag plus and Cl minus. How much were we given? Well, we were given 0.02 molar, right, of each, because it's in a 1 liter solution. So we can find our QSP, which again is the same exact expression as KSP, except notice how this equilibrium subscript is missing here. We're not necessarily at equilibrium. So let's find out where we are. Well, QSP turns out to be 4 times 10 to the negative 4, which is greater than our KSP, right? So in this case, we are beyond saturation. We have formed a solid precipitate of silver chloride. So the answer to this question is yes, AgCl will precipitate because we have added enough of their respective ions in this reaction to reach beyond saturation. Okay, now let's imagine they had asked how much silver chloride is going to precipitate. So it's actually not that hard to do this. Remember, we are in this situation here. We are beyond saturation. Remember, I used sodium chloride just as an example, but here we're dealing with silver chloride. So we're in a situation where we have some amount of silver chloride solid and some amount of dissolved silver plus and chloride minus ions in our solution. And they're essentially asking how much of it is in this solid state? Well, we know there's going to be a total amount of silver and a total amount of chloride in our solution, and it's going to be made up of the ions and the solids. So we can simply set up two algebraic equations here. We can say the total moles of silver are equal to the dissolved moles of silver ions plus the solid moles of silver. Remember, there's going to be some silver out here, some silver in the solid, and the same exact thing for the chloride. And we already know exactly how many silver ions can be out here because of the equilibrium constant, 1.8 times 10 to the negative 10. We solve for the equilibrium concentration of silver, and we get that to be 1.34 times 10 to the negative 5 molar, and since it's 1 liter, we know this is 1 mole. So we know that is the maximum amount of silver ions that can be out here in the solution. Any more than that, and they start to become solid in the solid state. Well, we know we added 0.02 moles of silver nitrate, so that's how many moles of silver we have total. We know how much of it is made up by dissolved silver ions because that's the max. That's how much we can have before it starts to turn into solid. So the rest of it must be solid silver moles. And it's the same exact equation for the chloride because they're in a 1-to-1 molar ratio. You can see here, there's one of these for every one of these. And you end up with 0.012 moles of each amount of element in its solid state. So that means we must have 0.012 moles of silver chloride. And generally in chemistry, when we ask how much, we're asking about a mass. So we can take this 0.012 moles of silver chloride and simply change it into grams of silver chloride using the conversion factor you can find on the periodic table. Silver plus chloride is 143.3 grams per mole. And you get that 1.72 grams of silver chloride were left as a precipitate. So see, not that bad.